Hi guys, welcome to assignment 3 for COSC 330-530. And in assignment 3, we're going to be working with message passing interface using our simulated cluster system here that's available through the server bubaki.une.edu. And we're going to be doing some matrix data processing. From the examples and some of the applications that we've worked with in this course, you're probably familiar with the idea of a data matrix. Basically, it's a two-dimensional structure, or it can be n-dimensional, but we've looked mostly at two-dimensional structures that contain elements that represent usually numeric values for processing various different problems. And in this assignment, you're going to be implementing what we call a convolution filter on a square matrix. Now, a convolution filter is basically a method by which we modify the values in our starting matrix. So here we have an example of a 4x4 element starting matrix by performing some operation on them that usually involves the neighbors or a neighboring region of values from the matrix around them. So in our simple example here, we've got our original data matrix, which is a 4x4 numeric matrix, and we've replaced every element by the sum of its immediate neighbors. So if we look at the top left-hand corner here, we can see that element at position 0, 0, we'll call that 0, 0, starting from the top, is replaced with the sum of its immediate neighbors here. So it's 2 plus 2 plus 3, giving us a value of 7. And so by applying that same operation, moving through the matrix, so again, if we move to the second element in the top row, we replace it by the sum of all of these neighbors around it, we adjust the value of that original pixel. And so this is used in as a step of many different processing algorithms, but the best real-world example is the blur filter that you can apply to an image. It's basically some sort of a weighted average calculated from a specified region from the surrounding neighbors. And if you're in the 500 level version of this course, the final assignment will involve calculating a Gaussian blur matrix for an image. So instead of using one matrix, you'll have a matrix for each row of pixel channel. But here today, we're keeping things fairly simple because we're going to be working with MPI, which can be a little bit tricky because the paradigm is a little bit new. So your task will be to build a convolution filter for a data matrix. It can be an arbitrarily sized square matrix that replaces each element with the mean of its neighbors. So it should be able to handle a matrix of any arbitrary size, and it should be able to handle a neighborhood of any arbitrary depth, assuming that the depth is less than the size of the data matrix that we're putting in there. So, for example, if we had a neighborhood size of 2, you would expect that for the pixel in the top left-hand corner, it would have all of the neighbors within 2 pixels covered off in there. So you'd end up with a neighborhood of approximately eight neighboring values there. And so to solve this approach, you'll have to have each process in your MPI program will calculate the results for consecutive rows or columns of the output matrix. So in our particular scenario, the output matrix will be the same size as the input matrix. So you'll need to divide that matrix up so that the consecutive rows are sent to each of the processes for processing, and remember that there'll be an overlap between the processes because the neighborhood will include input pixels that are calculated as output for another process there. So make sure that each process gets the minimum amount of data needed to complete the required number of calculations for its rows or columns. And it will then need to carry out this mean calculation for each element and return the resulting segment that it's calculated back to the main process or the master process. So for example, if the program is executed with 2 processes, the first process will calculate the results for the top half if we're distributing our matrix by rows, and the the second process will work on the bottom half. So basically, if we're working in a row arrangement here, the first process will look at the top half of the matrix, the second process will look at the bottom half. So fairly simple concept, and start from there and build up. So then work on adding an arbitrary number of processes to your solution to divide that up. So to achieve this, we've already looked at some matrix handling code before. Lecture 17 introduced a little library that works with binary files that store our matrix data, and there's some examples there. So the getMatrix.c example shows you how to call on the function. So in this case, we're calling the getSlot function from our library, from our matrix.h library, to access elements of data from our files there. And the matrix.c and matrix.h library there have all of the supporting functions to do that. So take a look at those. You're free to write your own code to do this, but if you use that as a starting point, it'll probably save you a little bit of time. It's important that each process is only sent the minimum data to do its calculation. I don't want to see you copying the entire matrix to every process, because the idea of MPI is that it's scalable. So you can work on really massive data sets, and we achieve that by minimizing the communication overhead. So if you're using your send and receive function, for example, to send out your rows of data, you want to minimize the data that has to be sent through those functions. And elements around the edges will have fewer elements than those in the interior of your matrix, so you have to have special cases to handle those. So for example, the neighborhood in our extreme left values here has different number of neighbors to the ones in the interior here. So you'll need to write code into your program to handle that. And the partial results should be communicated back to the master node, as I mentioned. Again, we want to minimize the overhead of communication there. So as usual, we've got our tentative marking scheme here that has all of the things that your solution needs to achieve. So go through, and you should be used to those by now. Go through and make sure you cover off on all of those items. You'll be submitting your program through the submit application. Now it's installed on Turing, so it's not on Bubaki. So what you'll need to do is, when you go into the submit program, upload all of your files, and then when you record your submission script of your solution compiling and running, the first thing you need to do in that is SSH into Bubaki. So you'll SSH into Bubaki once you've started creating your script. Do your compilation, run your program, then exit out, and then exit out of your script, and it'll record everything that you see on the terminal. So it's just an extra step there to remember when you carry out your submission. So this problem, although it seems kind of simple, once you throw MPI into the mix and the need to communicate those data items around, it can become quite complex. So make sure that you start early and start with the simplest possible case. So start with 1 and 2 processes, and then work up to arbitrary numbers of processes on your problem. So if you have any questions, please send them through. Otherwise, good luck with assignment 3.